Why is the concept of surface area and volume important in our daily lives? Gulliver's Travels, written by a British writer named Jonathan Swift, is a four-part satire novel. The main character, Lemuel Gulliver, the British sailor, would explore different but magical countries after each shipwreck at sea. The story begins by Gulliver discovering himself as a giant in an island called Lilliput, inhabited by tiny people less than 6 inches tall. The second part is when Gulliver ends up on Brobdingnag, discovered by a very tall man whose step is as wide as 10 years. Here, as a small person, he understands the problem of comparing big and small. Setting out again, in part 3, Gulliver visits many countries like a flying island, where he encounters a person devoted to thinking, a person who studies magical worlds, and a magician that can bring back the dead and the past. In the last part of the book, he is abandoned on an island or horses. Here, he comes upon yahoos, a creature born out of illness, foolish, and evil behaviors that resembles human beings. He also meets Howans, a race of talking horses that have odor, polite, and clean, all living in peace. Most of the readers may be only familiar with the first and second part of the book, where he talks about short and tall people. Here, 1 feet in the small people's island is equal to today's 1 inch, and 1 inch in the giant's island is equal to today's 1 feet. But since 1 feet is equal to 12 inch, everything in Lilliput is 1/12 of our world, while in Brobdingnag, everything will be 12 times bigger. The numbers presented in this book is the result of accurate mathematical calculations. How big is Gulliver's meal portion compared to an average person in Lilliput? How much clothing fabric was needed to make Gulliver's clothes? How big is an apple in Brobdingnag? Most of the calculations in Swift's book was quite accurate. For example, since Lilliputians are 1/12 of Gulliver, their body volume is 1/1728 of Gulliver, where 1728 comes from 12 times 12 times 12. Here, a meal for Gulliver would equal to 1728 servings of a Lilliputian. We can calculate Gulliver's clothing size based on similar calculations. Since Gulliver's body surface area is 144 times that of a Lilliputian, that means we need 144 times more of clothing fabric and tailors. The book claims that Lilliputians hired 300 tailors to finish the job. Here, because the job needs to be finished quickly, they hired us twice as many tailors to complete. Mathematics is essential in wrapping gifts or painting your wall. When we cook ramen, the noodles are very wavy. Have you wondered why? Ramen is a noodle pre-fried in oil. You can cook them with soup and boiling water. Recently, some new noodles are not fried. Most ramen is packaged with seasoning oil and powder. You can enjoy the noodle by putting all of them in hot water for 3 to 4 minutes. However, unlike other noodles, ramen noodles are curly. This is to contain more ramen in a small bag. Wavy texture helps to cook better by maximizing the surface contact with oil. Afterwards, the curly texture helps oil to escape faster, too. The noodles will cook better if the hot water comes in contact evenly between noodles. curly texture not only looks more appetizing, but it's also easier to lift them with chopsticks. During transportation, the curly ramen noodles are less likely to be damaged because they can withstand higher pressure. The concept of surface area and volume can be easily found in our daily lives. Understanding the surface area, volume, and density of figures can make our lives more convenient. This is why we study them. Figures consist of dots, lines, and planes. A line is defined as an infinite extension of a line of points. A plane is an infinitely many intersecting lines. To understand the surface area and volume of figures, one must first comprehend the building blocks of geometry, point, lines, and planes. One must also understand the exact definition of mathematical terms. For example, the volume is the amount of space taken up by an object, whereas capacity is the measure of an object's ability to hold a substance. It's imperative to also understand different units of measurements for figures. Space refers to a position where humans and objects are located. It is also a place that humans and objects can move. The existence of space was always interpreted in terms of an object and its movement and humans and their movement. According to ancient atomists, space is completely empty. Here, if the surface area can be defined as the fundamental of an object, then the object and the space are the same. A space is where objects can interest. Scholars such as Aristotle, Newton, and Leibniz debated whether space and objects exist independent or interdependent of one another. To understand space in a different light, we must first think of space in terms of humans and human activities. For humans, there is space for daily life, environment, and city. Here, space should be defined differently from the object and its movement. For example, the distance between two people across from each other can be seen as more than the physical distance. The distance can reflect the level of intimacy and social status between the two people. Capacity refers to the inner space size of kettle and bottles. When comparing capacity, we use terms like big or small. The units for capacity is liters, where 1 liter equals to the volume of a cube with a side length of 10 centimeters. The volume of a cube with a side length of 1 centimeter has the volume of 1 milliliter, or milliliter. 1,000 liter is also written as 1 kiloliter, or kiloliter. Then what was the unit used for capacity in East Asia? Day and mal were the units of capacity used in ancient Korea to measure grains such as rice and beans. 1 hope was approximately 180 milliliter, and 1 day is approximately 1.8 liter, and 1 mal is approximately 18 liter. In other words, 1 hope is 1/10 of 1 day, and 1 day is 1/10 of 1 mal. What is the relationship between density and volume? King Herod II, the king of the most affluent city in ancient Sicilia, Syracuse, hired a mathematician named Archimedes to see if the crown is pure cold. However, he couldn't find a way to ensure that the crown was pure cold without damaging the crown. Archimedes, who struggled with this problem, went to take a bath. Without thinking, he went into the bathtub filled with water. Then he saw that the water spilled over the tub. It's obvious that when you put an object in a bowl full of water, the water will spill over. Here, Archimedes discovered that the volume of displaced water must equal to the volume of his body. That's how he thought that he can probably estimate the exact volume of the crown if he can put the crown in a container and measure the volume of displaced water. Excited, Archimedes jumps out of the tub and yells "Eureka" as he walks down the street, naked. This anecdote is very famous. The term Eureka means "I have found it" in Greek. Archimedes knew that the volume of cubes or even shaped figures such as gold and silver bars can be calculated by multiplying length, width and height. Since gold was high in density, its volume would be bigger than the silver of the same volume. Archimedes calculated the weight of the crown precisely to prepare a gold and silver bar of the same weight. In front of the king, he sank the gold bar in the water and measured the volume of the displaced water. Then he repeated these steps with the silver bar. Here, the volume of water displaced by the silver was larger than the gold. When he put the crown in the water, the volume of water displaced was a little bigger than the volume of the gold. From this experiment, he concluded that the crown is not pure gold. He took a further step to calculate how much gold was replaced with silver. Water is one of the most important components on Earth. Without water, or without its characteristics, we'll face a great tragedy. The importance of water is evident as almost 70% of human body is water. Water is a solvent that can dissolve various substances. Its molecule consists of 2 hydrogen and 1 oxygen atom. Liquid water consists of many water molecules. In a water molecule, the hydrogens have a partial positive charge, and the oxygen has a partial negative molecule. Because the oxygen attracts electrons, there are relatively more electrons near oxygen. The oxygen in a water molecule attracts other electrons in hydrogens, but it also attracts electrons of other hydrogens from another water molecule, causing to form a light bond. This weak bond is called hydrogen bonding. The boiling point of water is very high compared with the same molecular weight. Normally, the boiling point of liquids is similar for the same molecular weight, but for water, the boiling point is higher than other liquids due to hydrogen bonding. Most liquids decrease in volume in solids. However, the volume of water increases when it's transformed into a solid. We can easily witness the force of water molecules whenever we see the broken water pipes in winter. As mentioned, the hydrogen bonding causes water to have higher surface tension. Here, the surface tension refers to the tendency of the fluid to shrink into the smallest surface area possible. That's why a paperclip is floating on the surface of a cup of water. A water strider can also walk on water due to the water's high surface tension. Whenever you go to the beach during summer, you may wonder, why is the temperature between the water and sand different? After all, they are exposed to the same amount of sunlight. That's because water and sand require different amount of energy to reach the same temperature. The amount of heat needed to raise the temperature of the sand by 1 degree Celsius is less than the amount needed to raise the temperature of water. Let's take a look at another example. What happens when you heat the same amount of water in cooking oil? After a certain period of time, the temperature of cooking oil will be higher than water. This is because the amount of heat required to raise the temperature of the substance by 1 degree Celsius is different for every substance. The specific heat is the amount of heat per gram required to raise the temperature by 1 degree Celsius. The specific heat is different for each substance type. For example, the heat required to raise the temperature of 1 gram water by 1 degree Celsius is defined as 1 calorie, or calories. The specific heat of water, in this case, is measured as 1 calorie per gram times degree Celsius. The specific heat of sand is 0.19 calorie per gram times degree Celsius, which is about 1/5 of water. The smaller specific heat means faster the temperature will rise, but also means that it will lose heat faster, too. Another unit used for specific heat is joules, and 1 calorie equals to 4.2 joules. Now you understand why the temperature of water rises slower than the sand with the same amount of heat. Then let's think about what would happen if the temperature is lowered by 1 degree Celsius. The substance with lower specific heat will have a faster drop in temperature, as it loses heat faster. That's why the water feels warmer during cold winter. The temperature of the water drops slower compared to the surrounding objects. The specific heat of cooking oil is less than water, at 0.3 to 0.4 calorie per gram times degree Celsius. That's why we can lower the temperature of the frying pan faster with cooking oil than water. Because water molecules are connected with hydrogen bonding, the heat of vaporization is much larger than other substances. The heat of vaporization refers to the amount of energy that must be added to a liquid substance to turn into a gas. This means that more heat is needed for water to break the hydrogen bonding to turn into vapor. Therefore, water's boiling point of 100 degrees Celsius is higher than other substances. Density is calculated by dividing the mass of a substance by its volume. Similar to the specific heat, each substance has its own density. The unit of measurement for density includes gram per milliliter and gram per centimeter cubed. Most solids have a higher density as the molecules are very tightly located to one another. However, the distance between molecules in liquids is bigger than solids. This means that the volume is bigger, but the density is smaller. In addition, because the distance between molecules is bigger in gas than liquids, the density is extremely small. In conclusion, the density of a substance is the biggest in solids, followed by liquid and gas. But in water, due to hydrogen bonding, the volume of solids is bigger than liquids. Therefore, just for water, the density is the biggest for liquid, followed by solid, and gas. Generally, the density of solid and liquids would not change even if the temperature or pressure changes. However, for gas, as the temperature increases, the motion of the gas molecule becomes active. This would increase the volume but decrease the density. Of course, as the pressure increases, the volume will decrease, and the density will increase. Our bodies react differently to temperature changes. When the temperature rises, the body will start to sweat. But when the temperature drops, the body will shake and shrink. Likewise, substances will react differently to temperature. Most substances will increase in length and volume with the rise in temperature and return to the original state when the temperature drops. Thermal expansion refers to a phenomenon where an object receives heat and its length and volume change. It is often seen in our daily lives. This is why pouring hot water into a cold glass cup can break the cup. Because a glass does not transfer heat well, the inside of a glass cup exposed to hot water will start to expand, while the outer glass will not change, causing the cup to break. Then why does a substance expand with the rise in temperature? A substance is composed of smaller particles such as atoms or molecules. With heat, they will become more active, causing them to break further away. If the average distance between the particles increases, the length and the volume will increase, too. The ratio of volume in proportion to a 1 degree Celsius in substance is called the coefficient of thermal expansion. Each substance has its own coefficient. Bimetal refers to an object that is composed of two different metals with two different coefficients of thermal expansion. With the increase of temperature, a bimetallic strip will bend towards the metal with a lower coefficient of thermal expansion. When heat is applied to a bimetal made of brass and iron, the thermal expansion will cause it to bend towards iron. This property has been used in automatic thermostats or switchgears. Not all substances will expand with the rise in temperature, some would actually shrink. This is called the thermal expansion of the negative. Although they are rare, negative thermal expansion occurs only at a limited size and range of temperatures. Water is a typical example of negative thermal expansion. Water has negative thermal expansion at 0 to 4 degrees Celsius. When the water is cooled down to 4 degrees Celsius, the coefficient of thermal expansion becomes 0. With a lower temperature, the coefficient will be negative. Negative thermal expansion is closely related to the physical-chemical process of contraction with the rise in temperature. Why does water freeze from the surface? When the warm water cools down, a flow of water molecules called convection will form in water. When the temperature of the water is above 4 degrees Celsius, the volume will increase but the density will decrease. This is why ice will float. But if the water temperature is below 4 degrees Celsius, negative thermal expansion will cause the volume to increase. As a result, cold water with a smaller density will float to the surface. Once the water reaches 0 degrees Celsius, it will start to freeze from the surface. Now you probably understand why the density of water is the biggest at 4 degrees Celsius. Why does the volume of water increase when frozen? It's because of the unique asymmetric structure of water molecules. Why does the volume increase when the water is frozen? That's because the water molecule has a unique asymmetrical structure. The water molecule is in an open V shape. In a liquid, the water molecule is disorganized, which means the volume may decrease, but once frozen, the molecules will be distributed evenly, which would increase the volume by 10%. What would happen if the density of water is largest at 0 degrees Celsius and the volume decreased when frozen? The ecosystem will face a disaster. The rivers and lakes will start freezing from the bottom during winter, and ice pieces on the surface of the water will sink to the ground. The temperature of lakes and rivers will continue to decrease, causing the entire body of water to freeze. It means no marine life can survive. Thanks to water's unique characteristics, this will never happen. Where can we use these beautiful principles of nature? The most fundamental characteristics of gas compared to solid or liquid is that a gas can fill up a container of any size. Of course, filling up a large amount of gas in a small container will increase the pressure. This principle was used in steam engines. People always wanted machines to do their jobs. And some managed to realize this dream by using the steam of boiling water. Heating a sealed water container will produce the water vapor that will increase the pressure of the container. The steam engine uses the difference in pressure to move an object. This idea of moving an object with vapor pressure has been around for a long time. Archimedes is known to have produced a cannon that could fire with steam pressure, but it took more than 1,500 years to realize this idea. With the invention of the steam engine, people's lifestyle completely changed. The factory-based production method, where several machines are connected to the steam engine, became popular. This resulted in the mass production of goods at a lower price. Steam engine trains allowed people to move easily. Steam is still widely used today. Thermal or nuclear power plants must use turbines to produce electricity. Coal is used to boil water in coal power plants, but the heat from nuclear fission is used to boil water in nuclear power plants. Apart from this difference, most operating principles of power plants are the same. Vapor pressure is defined the pressure exerted by vapor as the result of the equilibrium of the speed of evaporation and condensation. Here, vaporization refers to the phenomenon where a liquid absorbs heat energy to turn into a gas. The vapor pressure depends on the temperature. The rise in temperature will cause the pressure to rise, the fall in temperature will cause the pressure to decrease. At the same temperature, if the volatility is higher, the pressure will be higher, too. For a liquid to boil, the vapor pressure must equal the atmospheric pressure. The motion of a molecule is more active as a liquid than as a solid, and more so as a gas than as a liquid. Such movement of molecules is caused by the absorption of heat energy. When the liquid transforms into gas, the heat absorbed from the surroundings is called the heat of vaporization or evaporation. For example, the heat of vaporization required to make 1 kilogram of liquid into water vapor at 100 degrees Celsius is 539 kilocalorie. Evaporation is the process of a liquid transforming into a gas. That's why wet laundries will dry up. Boiling is when both the surface and inside of the liquid changes into gas. Evaporation and boiling are examples of vaporization because both phenomena involves the absorption of surrounding heat. In the summer, you'll feel cooler after spraying water because the air will cool down as the water evaporates by absorbing heat. Vapor pressure is measured in units of atmospheric pressure. The International System of Units expresses the vapor pressure as the magnitude of the force acting on a unit area, or Pascal. When a force of 1 Newton is applied to an area of 1 square meter, the pressure is 1 Pascal. Sometimes, this unit is expressed in Newton per square meter. Pressure is the force exerted perpendicular to the surface of an object. The relationship between vapor pressure and volume can be described by Boyle's law. The volume of the gas varies with pressure. The higher the pressure, the smaller the volume. When the pressure is doubled at a constant temperature, the volume is reduced by 50%. If the pressure is tripled, the volume is reduced to about 33%. Since the volume and pressure are inversely proportional to the constant temperature, it can be expressed as P0 times V0 equals PV equals K, where K is constant. This is also known as Boyle's law. The bubbles formed in water will get bigger as they rise, because the pressure will continue to decrease. Balloons filled with hydrogen or helium gas will get bigger as it goes further up in the sky. Eventually, they will burst. As the altitude increases, the atmospheric pressure will be lower than the balloon, causing the volume to increase indefinitely. Boyle's law states that the volume of gas is inversely proportional to the pressure, if the temperature is constant. In other words, when the temperature is constant, the products of pressure and volume of the gas is constant. Then what are some examples of Boyle's law? 1. The volume of air inside the syringe will decrease when you press on the plunger. In other words, if the syringe is filled with air, with constant pressure, the volume will decrease. Here, as the number of collisions of gas molecules increases, the pressure inside the syringe will increase. 2. A rubber ball inside a decompression container will expand if the air in the container is reduced. Removing the air will reduce the number of gas molecules, causing the pressure to decrease. This will increase the volume of gas inside the rubber ball, causing the ball to expand. 3. In high altitudes, your ears will clog, known as ear barotrauma. The air pressure in high altitudes is lower, causing the volume of air inside the eardrum to increase, pressing harder on the eardrum. 4. When you climb high mountains, your bag of sweets will expand. As the air pressure decreases, the volume of gas will increase, causing the bag to swell up. 5. The rubber balloon gets bigger and bigger as it travels up in the air. In higher altitudes, the air is thin with lower pressure. This will cause the volume of the gas to increase and the balloon to expand. 6. The air bubbles emitted by divers in water will get bigger as they get closer to the surface, because the water pressure will decrease closer to the surface, causing the volume of air to increase. 7. If you run in sneakers with air cushion, the volume of the cushion will decrease by absorbing the shock. The principle behind these shoes is that the volume of air cushion will decrease by the pressure of feet touching the ground, thereby absorbing the shock. From these examples, we can conclude that when the pressure increases, the gas volume will decrease. Similarly, when the volume decreases, the pressure will increase as the number of collisions among gas molecules increase. Diver's disease, also known as decompression sickness, occurs when divers in deep water with high water pressure rises quickly to the surface. A rapid drop in water pressure causes the bubbles to form, followed by immediate increase in the volume of the nitrogen gas, causing acute pain by blocking the blood flow. It could be deadly, but you can prevent these gas bubbles from forming by controlling the speed to the surface. A beverage manufacturer must be able to maximize profit by reducing the production cost of a container. That's why the cans are cylinders, not rectangular or triangular columns. From different shapes of the same amount of material, sphere containers can store the highest volume. Of course, economic aspects are important, but one must consider the practical aspects, too. Sphere containers are difficult to transport or display. Then people began to use cylinder containers. For example, most chimneys are cylinders, too. The cylinder shape allows the emission of the maximum amount of smoke with the lowest cost. It is the shape that guarantees the best result with the least cost. Various units are standardized to uncover secrets and measure nature. The world is filled with things created to satisfy people's needs. An unflinching curiosity has led people to develop measurement tools that can observe nature. Numerous units were needed to record different measurements. But now, these unit measurements have standardized. It has become natural for everyone to live in a world with standardized measurements.